Welcome to this radar observation and plotting module. The main learning objectives of this program are how to set up and maintain a radar picture, how to use radar information for navigation purposes, the learning objective of this section is to give the trainees sufficient knowledge of fundamental principles of radar and knowledge and understanding of the factors that affect the reliability and performance of radar. The word radar is believed to have been derived from the phrase radio detection and ranging. For many people, radar is difficult to understand. However, its principle is simple. Short radio waves, like acoustic waves, are reflected by objects that come in their way. In the radar, a short burst of electromagnetic energy is transmitted, hits an object, and then returns. Since the velocity of propagation is known, it's easy to calculate the distance to the object. As long as we are able to measure the time from which transmission is started until the echo returns. The transmitted pulse must be short in order to distinguish between echoes located close to each other. On board a ship, the radar has two main tasks. One is to function as an aid to prevent collisions. As with the help of radar, one can see in fog and darkness. The other is to assist navigation, particularly at landfalls and when navigating in coastal waters or in archipelagos. Radio waves are electromagnetic wave motions of the same kind as those of light, and consists, like all other wave motions, of a train of crests and troughs. The wavelength is a distance between two successive crests of waves. By international agreement, electromagnetic waves of a length between 0.1 and 30,000 millimeters are known as radio waves. Frequency is another way to measure wave motion. Frequency indicates the number of crests which pass a fixed point per unit time. Frequency and wavelength are two terms that are closely associated. If the wavelength is long, that is, the distance between the crests is long, comparatively few crests will pass the fixed point per second, and the frequency will be low. If, on the other hand, the wavelength is short, more crests will pass the fixed point per second, and the frequency will be higher. Most marine radars transmit in the X-band, 3 centimeters, C-band, 5 centimeters, S-band, 10 centimeters, corresponding to approximately 9,000, 5,000 and 3,000 megahertz frequency. Each type has its advantages and disadvantages. For example, a short wavelength is preferred in shipboard radar systems because there is a relationship between the size of the antenna and the horizontal beam width. The larger the width of the scanner, the smaller is the angular beam width for the same wavelength. This radar block diagram can be divided into 5 main parts: antenna, with motor, gear, etc., which directs and transmits radio waves; transmitter with magnetron, modulator and trigger, which generate radar waves; receiver with mixer, amplifier, equalizer and video amplifier, which receive the reflected waves. Display unit, which measures the time and presents ranges and bearings in a suitable way for navigational purposes. Power supply with power transformer, which provide power to the various radar parts. It is not necessary for the radar operator to know all the details about each radar component. However, for safe and efficient use of the radar, a basic understanding of how a radar works, its compatibilities and limitations, is a minimum requirement for all navigators using radar in their work. The radar antenna is constructed in such a manner that it transmits the radio waves out in a concentrated beam. A motor turns the antenna in rotations, so the entire area around the antenna can be observed. The weak high-frequency radar echo signals, which return via the antenna to the mixer, are converted to lower frequency signals, which are amplified. Finally, the signals proceed to the display, where they become visible to the operator in the form of a radar picture. Two types of radar antennas are used on merchant ships today: slotted waveguide type and parabolic type. The slotted waveguide type is the most common nowadays. There are several reasons for this. Here we can mention the following. Because of the small front area of the slotted waveguide antenna, steady rotation can be maintained in strong winds with a relatively small antenna motor. The weight of the slotted waveguide antenna is much less than that of the parabolic type antenna, causing less wear and tear on the antenna gear. The main advantage of the parabolic antenna is the good sensitivity, which is far better than the S.S.G antenna. The radar receives power from the ship's main power source. If the ship's mains provide DC voltage, this must be fed to a converter, which changes the voltage to the input level required by the radar equipment. If the ship's mains provide AC voltage, this is fed to a transformer, which provides the required output. Radar echoes are displayed on a cathode ray tube. The CRT measures the time and presents targets, range and bearings in a suitable way for navigation. Several types of CRT are utilised: A-scan, or short persistence tube, plan position indicator, or PPI, raster scan display. The trigger transfers pulses at the modulator, which between pulses increases to a powerful voltage. These pulses are transferred to the magnetron. The magnetron converts the input into high-frequency oscillations. From the magnetron, the high-frequency oscillations are fed via a waveguide or coaxial cable to the transmitter-receiver switch. Because the waveguide is shared for both transmitting and receiving, a transmitter-receiver transformer is used. Its function is to act as a switch, to allow the transmitted oscillations out through the antenna, while blocking the signal to the receiver. When the radar echo signals return, its function is reversed, so that the signal passes to the receiver, while stopping outgoing signals from the transmitter. The duration of the transmitted radar pulse may vary from less than 0.1 microsecond to as much as 1.5 to 2 microseconds. Intervals between the pulses are typically between 500 to 4,000 microseconds. In the radar receiver, the incoming signal is fed to a series of amplifiers and further to a detector or demodulator, which smoothes out the signal. The greatest problem is to keep the noise level low. On the radar, the noise appears a speckled background on the screen and must be kept as low as possible for the navigator to see the weak echoes. The main task of the receiver is to amplify the reflected weak echoes and make them suitable for transmission to the indicator or screen. Two radar terms are often mixed or used incorrectly, namely radar scan and radar sweep. Remember this: a radar sweep is the transmission of one radar pulse only. A radar scan is one complete 360 degrees rotation of the antenna. During one scan, normally several thousand sweeps are generated and transmitted. In modern radar systems, both sweep and scan correlation may be used to filter away unwanted noise. Read the manufacturer's manual and do not mix the terms sweep and scan, as this can produce unwanted effects on the radar screen. The pulse repetition frequency is defined as the number of pulses transmitted per second. Long pulse equals low PRF, while short pulse equals high PRF. Long pulse means more power and longer radar range, but less resolution in range. Short pulse means weaker pulse, less radar range, but better resolution in range. Selection of pulse length may affect the radar range resolution in a negative way. The radar minimum range depends mainly on the following parameters: antenna vertical beam width, selected pulse length, height of antenna, installation of antenna, ship's trim. The radar minimum range is hardly ever a problem in practice when using the radar for traffic surveillance. The radar range will vary with changing weather conditions, however. During standard atmospheric conditions, that is 1013 millibar air pressure, 0 altitude and an air temperature of 18 degrees centigrade, the following formula can be used, where Rmax is radar horizon in nautical miles, H1 is antenna height in meters, H2 is target height in meters. In practice, during normal weather conditions, navigators can expect the radar horizon to be approximately 10% further away than the optical horizon. The most important parameters affecting radar range are antenna height, height of target, size of target, target reflecting area, material of target, shape of target, weather conditions. The following technical parameters must also be taken into account: transmitted peak power, wavelength, pulse length, antenna gain, noise figure, number of pulses per scan, wave guide loss, display parameters. Range discrimination is the ability of the radar to discriminate between two small objects close together in the same bearing. That is, display separate echoes. The further object must not be in the shadow of the nearer one. The most important parameters affecting range discrimination: selected pulse length, the size of the spot. If possible, short pulse and short range should be selected, and focus and brightness carefully adjusted. This animation tries to illustrate what may happen when two ships are close in range and the radar is operated on short pulse. On the radar screen, two echoes can be seen. As long as the ship at the longest range is not in the radar shadow of the nearer one. This animation shows the same situation, but the radar is operated on long pulse. On the radar screen, only one echo is visible. The range resolution is the radar's ability to distinguish between two targets close to each other, in same range or bearing. Bearing discrimination is the ability of the radar to discriminate between two small objects close together, at the same range but with different bearings. That is, the ability to produce two separate echoes on the radar screen. The bearing discrimination depends on the horizontal beam width of the antenna, the spot size. Correct focusing and brightness settings will improve the bearing discrimination. This picture tries to illustrate what may happen when two ships are close in bearing and the X-band radar with a narrow horizontal beam width is used. Two echoes can be seen on the radar, as long as the two ships are not hit within the same beam. This picture tries to illustrate what may happen when the same beam hits two ships. Only one echo is displayed on the radar screen. Bearing resolution is the radar's ability to discriminate between two targets located at the same range and close to each other. The radar's possibility to reproduce an area or a ship correctly and to discriminate between close-lying targets is limited and varies with different types of radar. The discriminating ability in range is usually 25 to 75 metres. However, the accuracy is lower on long ranges. The discriminating ability, laterally, is usually 1 to 2 degrees. Radar sets with a wavelength of 3 centimetres have, generally speaking, a better discriminating ability compared with a 10 centimetre wavelength. This is the situation on a ship entering a harbour, as seen on an X-band radar operating on short pulse. This is the situation on a ship entering a harbour, as seen on an S.S.G. 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 S.S.G Observe the big difference in ability to display details between the two radar types. This is the situation as seen on a ship sailing in a narrow channel, as seen on X-band radar operating on short pulse. This is the same situation as displayed on S-band radar operating on long pulse. Observe that the channel is closed in front of the ship. The target capacity to reflect radar pulses is dependent on the target's size, shape, and material. When a radar pulse hits a target, some of the pulse will be absorbed and some of it reflected. How much of the reflected echo will return to the scanner depends on the shape and the angle of approach, and the material of the target, that is, steel, fiberglass, wood, etc. Radar pulse reflection is subjected to the same laws as those for the reflection of light. The reflecting power of metal and water is higher than that of stone, wood, and ice. If, for example, the detection range of a target of metal is 10 nautical miles, then the range of a target with the same size and shape but made of stone is approximately 6, of water 9, and ice or wood approximately 5. The magnetic compass must have a safe distance from the radar because strong magnetic fields are generated in several parts of the radar. The exact safe distance is described in the radar manufacturer's installation manual, as well as in documentation provided by the classification societies. Normally, the safe distance varies between 1 and 5 meters. Nowadays, although most ships are equipped with a gyro compass, the magnetic compass is still the master compass on all ships, and thus should be taken good care of. Marine radars transmit energy of varying strength in form of short pulses or bursts. Pulsed power can produce biological changes not obtained with constant wave transmissions. At a short distance, transmissions from marine radars may pose a health hazard. Follow the instructions from the radar manufacturer closely and don't take any chances. When working close to a radar antenna, make sure that a warning sign has been placed on the radar console, clearly telling everybody that no startup should be attempted before the work in the antenna is completed or cancelled. Whenever the air humidity is abnormally high, which it is in fog, rain, snow and hail, a reduction in radar detection range should be expected. Those who have operated radar for some time realise that sea and rain can considerably disturb the radar picture. These disturbances can be quite serious, but are easily detected. Disturbances not readily identifiable are more serious, however. These phenomena have become well known during the last 2 or 3 decades. Therefore, only a brief overview will be given here. Those interested in more details about this subject may refer to handbooks and radar manuals for more information on this subject. We have normal transmission of radar waves when conditions are such that the radar range is approximately 10 to 15% greater than the distance to the optical horizon. Generally, one can say that normal conditions exist in areas with cold air masses. Generally speaking, the longer the wavelength, the greater is the tendency to bend round objects. Hence, you can expect the 10 cm radar to have a greater range than the 3 cm radar. When warm, moist air remains over cold water, the air is cooled from below and fog is often the result. Temperature and humidity will increase with altitude, and the radar wave will bend upwards, decreasing the radar range. This is called subrefraction. Subrefraction decreases radar range. With conditions of light wind and low clouds over cold water, we often get a condition called ducting. That is, the radar beam is reflected several times between the fog and sea surface. The radar range can be increased considerably. Ducting can be expected to take place when temperature inversion exists and the atmosphere is calm. With conditions of considerable ground fog, we can get a total radar blackout. The reason for this is that all radar waves are reflected from the top of the fog and cannot penetrate through the fog down to sea level. Favourable conditions for radar blackouts are present when stationary warm air masses are located on top of cold sea. If the height of the fog is less than the height of the radar antenna, a total reflection of the radar signal from the top of the fog may take place. There are several variations and combinations of the conditions illustrated in these figures. Be particularly watchful during conditions when warm air masses can be expected to move in over cold sea. When this occurs, together with rapid changes in air moisture content, the situation should be carefully observed. Sea clutter echoes are caused by reflection of the radar pulse against the sea waves. The reflection is spectacular, and conditions for the pulse to return to the scanner are favourable near the ship. At longer ranges, the beam will be deflected away from the ship. Marine radars are equipped with rejection systems to minimise the effect of sea clutter. This control is often named anti-clutter sea, or STC. Rain squalls and showers appear on the screen as a woolly mass. An intense rainstorm can be detected at a distance up to 25 or more miles. Thunderstorms give excellent echoes, but even drizzle affects the radar range and may produce light diffuse echoes. Echoes of ships or land inside the rainstorm will be obscured by rain and clutter, and targets beyond the rain area will lose some or almost all of their echo strengths. During weather conditions including heavy rain, thunderstorms, etc., the S-band radar is a better choice than the X-band radar. The two pictures clearly show the difference between the S and X-band radar during heavy rain, as displayed on a Raytheon radar with conventional PPI display. Radar interference will occur most frequently when own ship's antenna receives signals from another radar. These disturbances often take the form of fan-shaped broken lines emanating from the centre of the screen. Most radar equipment contains radar interference rejection circuits to eliminate this disturbance. False echoes and disturbances on the radar screen may have many different appearances and causes. Some faults can affect the accuracy, so whenever disturbances are observed, be especially aware of this possibility. If the radar signal is reflected from objects on board own ship in such a way that the pulse hits a target, we may receive a false echo at almost the same distance as the real target, but in a different bearing. This false echo will often be located in own ship's blind sector. The navigator should know exactly where own ship's blind sectors are located. This is important in order to take actions to minimize the effect of the blind sectors. Multiple echoes can be created by a reflection between own ship and an object before the scanner finally collects its energy. On the PPI, we will see a line of targets on the same bearing and with equal distance between them. The true echo is the one closest to own ship. The shapes of multiple echoes are less defined than that of the original echo, and they are weakening in intensity outwards. Reduction of gain and clutter will remove the false echo before the true echo. Side echoes are caused by the side lobes, which are unwanted beams radiated by the scanner in a different direction to that of the much stronger main lobe. Nearby targets are picked up by the side lobes as well as by the main lobe. The effect of side echoes will only be observed at short ranges. Side echoes appear as concentric arcs round the centre of the screen. Reducing gain carefully or increasing, anti-clutter C will normally remove the less powerful side echoes. It is impossible to design a scanner without side lobes, although the construction of an aerial affects the magnitude of the side lobes. However, today many slotted waveguide scanners have almost eliminated the visual effects of side echoes. Blind sectors are caused when the antenna is not placed at the ship's highest point. All structures above the antenna will create blind sectors on the radar screen. Objects within these sectors will normally be invisible on the screen. All navigators should be familiar with the radar blind sectors on their ship. It is relatively easy to plot the blind sectors if this is done during a period with a lot of sea clutter. The blind sectors can be seen as distinctly dark sectors in the sea clutter area. Plot each sector on a plotting sheet and place this so it can easily be seen from the radar observer's position. When the heading marker on the radar screen does not exactly tally with the ship's heading, or in other words, when the echo from the target straight ahead does not lie exactly on the heading line, then we have a heading marker error. Heading marker errors may have serious effects on the radar picture and have been the cause of many collisions. Naturally, this error should be paid attention to and checked regularly. The error caused due to incorrect position of the heading marker contact or electronic sensor in the scanner housing is constant. As we have seen, the radar waves transmit in a straight line. A radar coastline echo, or any other object's appearance, will be determined by the topography. The radar picture can be quite different from the map. For example, the radar picture at low tide will be very different from that at high tide, if there is a large difference between high and low water. Knowledge of the topography effect on the radar picture can be of great importance whenever own ship's position determination must be based only on information from the radar display. Another important reason for the difference between the sea map and the radar image is the radar range and bearing discrimination parameters. That is, how much the radar magnifies the echo in range and bearing. The sweep centre, which on the PPI indicates own ship, must coincide exactly with the cursor centre of rotation to achieve a correct bearing. If this is not the case, the fixed cursor must not be used. If the radar is equipped with an electronic bearing line, this can still be used to obtain correct bearings. In this illustration, we try to visualize the effect of the centering error. Naturally, these types of errors should be paid attention to and checked from time to time, because if unnoticed, it can be perilous. On this illustration, position C is the cursor centre, and position S is the sweep centre. The figure shows the bearing errors obtained for a vessel approaching on a steady head-on course. The bearings, changing from 7 degrees to 37 degrees, indicates a noticeable bearing change to starboard of own ship. This can produce very dangerous situations during reduced visibility conditions. You have now completed this lesson, and all I ask is a tall ship and a star to steer her by. Bon voyage!